Okay, let's start. Okay. Um, so until now, we have seen the definition of what we mean by probability spaces. We have seen what we mean by uh, uh, by a random function on a probability space, how the random function induces a measure on the real line, and this measure is captured by the cumulative distribution function, the CDF. In particular, if the random variable x is an absolutely continuous random variable, um, so let me write this down. So this be a probability space, and we have a random variable uh, to R. And if the distribution is used by uh, x, if mu x is absolutely continuous with respect to m, which is the Lebesgue measure on R, um, then of course um, the random variable x would permit a probability density function. And so this probability density function, which we'll often denote by P, small letter p, as opposed to capital letter F, which will be the cumulative uh, distribution function um, subscripted by x. So px is the density function of x, and this is just the the Radon-Nikodym derivative. Well, what this simply means is that um, the probability of x lying in any A, where A is some uh, model subset uh, of R. So what this means that this is just equal to integral over a d mu x, but this is just equal to the probability density function, and then you just have the standard Levitt measure on R. Right. So we saw last week uh, about uh, uh, about um, about these random variables which do not permit density functions. In particular, if a random variable is discontinuous, it will not admit a um, it will not admit a uh, distribution function. But continuity itself is not sufficient to guarantee that the random variable would admit a uh, would admit a density function. Um, we need something more. This is the notion of absolute continuity. Um, so today we are going to look at some standard random variables that occur in practice. Um, Most of these random variables are probably things that you have seen before. We're going to look at we have looked at before the Bernoulli random variable and the binomial random variable, which was covered in the previous weeks. So today we're going to look at some continuous random variables. So those were discrete random variables. We're going to now look at these continuous random variables. So in particular, we're going to look at the uniform uh, random variable. Then the exponential, the um, the normal distribution, and the gamma distribution. So start off first with the uniform random variable, which is denoted as generally denoted as u0 comma 1. But in reality, you can have a the random variable to be some u a comma b, where a is uh, where a is less than b. So the sort of well, in this case, uh, the the probability density function of this u a comma b is denoted as is basically equal to um, uh, graphically this looks like something like this. You have 2 points a and b, and uh, the probability density function is a piecewise constant function. It is supported entirely within this interval a comma b, and within this interval a comma b, it is equal to 1 by b minus a. A special case, of course, is the is u0 comma 1, where this is distributed on 0 comma 1. Okay. So hopefully this is like very clear. Um, now, now let's look at some problems based on just this uniform random variable. In particular, um, let me pose this question. So let's look at this problem. Let x be a let x be a continuous random variable having a CDF of f. Okay? Now, what is the what is the distribution of f of x? I hope the question is clear. You have a random variable x, and you're taking the CDF of x, which is capital F. Now, what I do is that I consider the random variable f of x. This is a perfectly legitimate random variable, and I ask you what is the distribution of this random variable f of x. Right. So now, okay. So how do we start to answer a question like this? Um, okay. So if x is a random variable and you have some function h from R to R, assume h is continuous, and if I ask you what is the, or rather, how is h of x distributed? Uh, so then what you do is that, well, you look at the probability. Let's say, um, so f of a capital H of x at some a is the probability that h of x is uh, is less than or equal to a, right? Uh, and then of course you look at the set of uh, and then of course this is equal to probability of x belonging to the set h inverse of of minus infinity comma a. Okay, so this is the sort of theoretical way. Uh, uh, so I mean again, the when we're talking about h of x gets the distribution function of x pushed forward by h, right? So so this is just equal to mu of x of h inverse of minus infinity comma. Now, in our case, it is given that this h is the distribution function of f itself. Okay. Now, first of all, is h continuous? Sorry. Now, is f continuous? So, if x is a continuous random variable, f of x, its CDF function, would also be continuous. Now we are interested in computing, so let's call this y. So y is equal to capital F of x, and we're interested in computing the distribution of y. Now let's look at the um, the limits of y, right? So so what does y vary from? So notice that y varies from exactly 0 to 1. Okay. Now, furthermore, what is the distribution of y? So let us try to compute fy at some point t, where this t belongs to 0, comma 1. So fy of t is the
Say
probability.
uh,
Yes.
one is close bracket now, and 0 to 1 probability. सर दोनों क्लोज ब्रैकेट में होगा या ओपन ब्रैकेट?
कहाँ पे?
t belongs to
इसमें
0 1.
t belongs to 0, comma 1. Is that what you're asking?
Yes.
हाँ 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 uh, right. You can say t is from the close bracket 0. Yeah, that's fine. Um, right. So probability of f of x. So this is the probability that f of x is uh, less than or equal to t. Right. So now, well, what is the probability that f of x is less than or equal to t? Right. So for that, let's kind of think about um, the CDF of x itself. So the CDF of x, let's sort of draw uh, like an illustrative diagram. Let's say the CDF of x varies something, right? And so it varies from 0 to 1 exactly. And you have a point over here, which is, let's say, t. This is this height t, and you can of course ask the question that um, so because x is a continuous random variable, there is going to be so the solution of fx equals to t uh, is basically going to be is going to have solution. Okay, because x is a continuous random variable, and therefore f of x is also continuous. Now, now let's take some a where a is equal to uh, uh, let's write a uh, bracket t. So a bracket t is sup of is equal to sup of x such that f of x is equal to t. Okay. Now you might think, okay, why is there a sup? Because well, uh, the CDF function need not be monotonically increasing at t. In fact, you could have something like this. You could have uh, something like this. Right? So t could need not be just one value, but could be an entire set of values. Yeah, but t is always going to. But this f of x uh, is equal to t is always going to be a is always going to be a compact function. Okay, it's in fact going to be a compact interval. Okay, and you take the rightmost point of this interval, which is a of t. Now, now f of x being less than or equal to t is is equivalent to x being less than or equal to a of t, where a of t is defined as follows, right? And so the probability of x being less than or equal to a of t is is equal to t. Why? Because the probability of x being less than or equal to t is precisely equal to the cumulative distribution function of uh, of x evaluated at the point a of t. But at this point a of t, f of x is equal to t. Yeah, I mean there is a reason why I kind of use the open brackets instead of the closed brackets. I think I'll stick to that. Uh, so the reason why I'm kind of using the open brackets instead of the closed brackets is that if you take t to be equal um, to one, right? So then, I mean, uh, then this at becomes equal to infinity, right? And that makes things a little bit tricky. But that would not cause us a problem. So let's keep this t to be varying in the open interval. Right. So the probability of f of x being less than or equal to t is the probability of x being less than or equal to a of t, uh, which is just equal to t. So it follows that f of x is the uniform random variable from 0, comma 1. Right. So that's like a nice way in which the uniform random variable shows up. Okay. So this is a very interesting kind of example because if we ask you this question that how do you how do you in practice um, how do you in practice simulate a uniform random variable? So what do you mean by simulate an uniform random variable? So you have to create a uniform random variable, right? Um, like for instance, if I tell you, okay, simulate a Bernoulli random variable uh, uh, with probability with parameter half. Okay, so that's like saying that okay, I'm going to take a coin which is fair coin, and I can sort of toss that coin, and that gives me a way to generate this. this Bernoulli random variable. Now, if I ask you how do you, in practice, generate a uniform random variable, the thing is as follows. You start with any continuous random variable. Take any continuous random variable. It could be a Gaussian distribution. It could be an exponential distribution. Start with any random variable x, which you know how to simulate. Okay, so that could be so that could just be a normal distribution. Okay, and once you have the normal distribution and once you have that random variable with you, you compose the random variable with its CDF function. So you know x, and you know if you know f of x, then f of x is going to be the uniform random variable. So this is one way in which the uniform random variable can be generated in practice. Okay, hopefully this is clear.
Yes, sir.
Now let's take another example. Um, this is with respect to this I'm kind of leaving as an exercise. Um, So you have you have a fair coin with you. There is a fair coin, which sort of is the Bernoulli random variable with probability half. So it's B with probability half, uh, and you toss this coin n times. Okay, and so assume that each toss is uh, is independent of the other. Okay. Now, now you do this sort of translation as follows. Um, right. So, of course, uh, your base your probability space is just h comma t, uh, the Cartesian product taken n times. So h cross t to h cross t n times, and you define a map from omega to the open interval 0 comma 1, which is defined as follows. Um, for any word that is given, say W is equal to W1 up to Wn is any uh, combination of head and tails. So let's say, uh, suppose, say, uh, omega is equal to 1010 n times. You define a map from this thing, which is defined in this way. Um, so omega 1, omega n this map goes to um, uh, 0 point, um, 0 point A1, A2 up to AN. And how is this? So if omega 1, so if uh, where where AI is equal to 1, if omega I is head, and AI is equal to 0 if omega I is equal to tail. In other words, let's take a small example. If you, let's say n is equal to 3, and you have some combination which is head, tail, head, then you will send this head, tail, head to 0.101. Okay. Uh, but this number, 0.A1, A2 up to AN, is represented in base 2 digits. So I hope you understand what is meant by binary digits. So essentially, what I'm doing is that whatever I get, head, tail, head, I'm kind of translating it into a binary number. Uh, so this is how my binary number looks like. Okay, right. So essentially, what this map does is that this map actually defines a random variable. Okay. Um, so this map defines a random variable. Because this is n times, I'm going to subscript it by omega n. So it defines a random variable xn from omega n to 0, comma 1. Now you have to show that as n tends to infinity, uh, xn's converge to the uniform distribution 0, comma 1. In other words, the distribution of xn, what this means, I should write over here in distribution. What this means is that the distribution of x of n will tend towards u0, comma 1, n tending to infinity. This is what needs to be proved. Okay, I'm leaving this as an exercise. It's not hard to prove this. Okay. Um, okay, so that's this is all about the uniform random variable. Now I'm going to talk about, let's say, the exponential random variable. Just give me 1 minute. Right. So the exponential random variable is a random variable whose density function uh, small f of x is equal to lambda times e to the power minus lambda x if x is greater than or equal to 0 and is 0 if x is less than 0. So an exponential random variable is always um, is kind of parameterized by this lambda. A lambda is some positive constant. Now uh, the um, the CDF of x f of x is and this is just equal to um, 1 minus e to the power minus uh, so this is some a goes up to a e to the power minus lambda a for a greater than or equal to 0. So the exponential random variable is a random variable which occurs very frequently in practice because it often turns out that when we are modeling events, um, then it often turns out um, that these events are best modeled via exponential random variables. Exponential random variables have this so-called memoryless property, which states that the probability of x being greater than s plus t, given that x is already greater than s, is just the probability of x being greater than t. Right? Okay. Now let's look at some problem. Just give me 1 minute. I'm trying to come up with a problem. Okay, so let me introduce uh, uh, a slightly different concept, which is an interesting thing, and which kind of motivates what this lambda represents in an exponential random variable. So as I said, an exponential random variable often captures this so-called thing called when a particular event will happen. So you have uh, let's say you have some let's say you have a um, like a let's say you have a clock, okay, and you ask, okay, when will this clock fail? Or you can ask when will a particular hazard occur? So these are kind of questions like these are sort of motivated by this thing called hazard rate. So I'm just going to define that term over here. I'm going to then pose some problems. Uh, yeah, some of these things that I'm going to discuss here are not strictly what you'd find in the course lecture notes. So uh, yeah. So the hazard rate is uh, uh, is a function. So you have a random variable. So uh, let's say x is a random variable, and so throughout today's discussion, x will we're going to deal with nice random variables, all such random variables which are continuous, and more than that, they admit probability density functions. Okay. So I'm going to skip. I would not mention continuous. I would not mention things like having a density function and so on. They will be assumed in today's discussion. So let's say x is a random variable which has a density function of small f and a CDF of capital F. So then the hazard rate is defined as follows. It's defined as lambda of t is equal to uh, f of t by 1 minus f of t. Okay. Now, well, what is this? Uh, Okay. Okay. How to interpret this particular expression? Uh, so say x is some random variable, and let's say x is a random variable which models uh, something. Okay. Let's take an example. Say uh, x models the time when um, when a car breaks down. So you have this car, and you x is a random variable which models the time when the car will break down. Okay, x is obviously a positive random variable. So now, if we ask the question, what is the probability? What is the probability that um, Right. So what is the probability that uh, X will last for um, for a time of delta t? So let's say what is the probability that um, that X uh, will be from t to delta t, given that X is greater than t. So that is just equal to the probability of X belonging to t plus delta t. Uh, sorry, maybe it should be written as that t comma t plus delta t. Given that X is divided by the probability that X is greater than t. Right? This is just the definition of conditional probability. Now, of course, if you take uh, limit delta t tending to zero, so limit delta t tending to zero, this probability uh, is this quantity on the top will be equal to the density function f of x at t multiplied by delta t, and uh, and here you have uh, the probability of x being greater than t. Right. So, and this is equal to the hazard rate at time t multiplied by delta t. Okay, approximately speaking. So uh, lambda t is like a conditional density function. It indicates what is the time that the car will last for uh, a time of delta t, given that uh, uh, it basically models what is the time that the car will fail uh, eh, from time t to delta t, given that it has lasted till time t. Okay. So it captures the hazard rate. Okay, so if I have a car which has not broken down till time t, uh, what is the conditional probability that is going to break down now? Okay, so that's the hazard rate. Now what is the uh, hazard rate for x when x is exponentially distributed? So let's just write this hazard rate for x when x is exponentially distributed. Well, so that is just equal to lambda times e to the power minus lambda t by e to the power minus lambda t, which is just equal to lambda. Hence, you can also kind of see this from the membraneous property, that probability of x being greater than of, uh, well, not necessarily. Let's keep it like that. Okay. Um, hmm. So this lambda term in the exponential distribution, it has an obvious meaning. The lambda is the hazard rate for whatever you're trying to model. Um, Now the hazard rate. Now the thing with the hazard rate is that if you know the hazard rate of a random variable, you can recover the distribution. So um, we can, let me write it down. We can recover the distribution from the hazard rate. Well, how's that? So the hazard rate lambda t is equal to um, is the density function. So the density function, you can write it as uh, f dash t by 1 minus ft. Okay, so now you can integrate both sides, and if you so then you get log of 1 minus ft is equal to minus of integral lambda t dt plus uh, yeah, which gives us this f of t to be equal to 1 minus e to the power minus integral 0 to the lambda t dt. Okay, so if you know the hazard rate of a random variable, you can get back the distribution function. Okay, now it's a nice sort of theoretical exercise to take a random variable and try to compute its hazard function. So this is like an exercise. Uh, compute uh, the hazard functions, the hazard rates for standard continuous random variables. Okay. Um, with that, I hope things are clear. Uh, with that, let's look at the normal and the common distribution. Let's first talk about the gamma distribution. Uh, um, so a gamma distribution X, which I'm going to denote as, let's say, gamma, it takes two parameters, A and lambda, uh, both greater than zero, and its density function f of x is uh, is equal to lambda times e to the power minus lambda x, lambda x to the power alpha minus 1 by gamma of alpha. Okay. So this gamma of alpha comes from this so-called gamma function. Okay. And the gamma function is defined in this way. Uh, Gamma of alpha uh, is equal to uh, integration 0 to infinity x to the power alpha minus 1 e to the power minus x dx. Okay. And if alpha is a positive integer, then of course we can show that gamma of alpha is equal to alpha minus 1 factorial when alpha uh, belongs to n. Now you can easily check that this is a valid distribution function uh, because if you do an integral and if you substitute lambda of x, if you do the variable substitution where you put lambda of x equals to some z something, then so integral of f of x dx, substitute uh, substitute lambda x with z, uh, and then you can show that this uh, uh, that the term on the top, the integral of that would be equal to gamma of alpha, and so you have the integral uh, to be equal to 1. Now, now the um, now the gamma distribution occurs quite often in practice. Uh, so, so I'll just tell you when, or rather, how uh, the gamma distribution naturally arises. Um, so let's say you have events, okay, and Just give me 1 minute. I'll be just back in 1 minute. Yeah, okay. Thanks for waiting. Uh, yeah, so how does the gamma distribution arise in practice? Okay, so let's say you have a number of events that are taking place. Okay, uh, so uh, so think of these events as being the time at which these events occur as being random variables. Let's say x1, x2 up to xn, and think of these. Um, Not necessarily up to xn. Let's say you have like a countably infinite number of events, and each of these events can occur at any time t, and the occurrence of these events are independent of each other. Okay, So that uh, so that we keep track of a random variable which we're calling NT, where NT counts the number of events that have occurred uh, that have occurred uh, till time t. Okay, and NT is modeled. Right, NT is modeled by a Poisson random variable in with parameter lambda t. That is the probability of NT equal to n is equal to e to the power minus lambda t, lambda t to the power n by n factorial. So now, if we ask that what is the probability that NT is is greater than or equal to n, so uh, that is equal to sum over of probability of NT equal to I, where I runs from n to infinity. That is just equal to sum over of e to the power minus lambda t to the power I by I factorial. And it can be shown, not a difficult exercise to show that if we differentiate this expression with respect to time t, uh, this um, gives us uh, the density for the yeah, it gives us the density for the gamma distribution um, in parameters n comma lambda. Okay. Um, Finally, let's look at um, the normal distribution. Yeah, denoted as, let's say, n of mu comma sigma squared, which is the mean and the variance. The density function is defined as um, f of x is equal to 1 by root 2 pi sigma e to the power x minus mu squared by 2 sigma squared. Now, this is obviously the ubiquitous uh, distribution that uh, most of us have seen. This is the density function looks like um, uh, this bell-shaped curve, which is centered at the mean, which is mu, and the variance is equal to sigma squared. Let's look at one problem which is related to the normal distribution. So given the standard normal random variable z, so that means that z is um, n0 comma 1. The mean is 0, the variance is 1, and we're given a differentiable function g. Okay, and we have to find the following parts. Now it should be clear that the second part directly follows from the first part, right? Why? Because well, expectation of z to the power n plus 1 is expectation of z times z to the power n. So if we set g of z with the function z to the power n, then of course it follows from the first part that this is going to be equal to n times expectation of z to the power n minus 1. Right. And this gives us an iterative formula to compute expectation of z to the power 4 because, uh, well, you need expectation of z to the power 0, which is 1. From there, you can compute expectation of z to the power 2. And from there, you can compute expectation of z to the power 4. So this gives us a nice iterative formula to compute the expectations. So, uh, so B and C should be clear. I want to prove part A. Show that to show expectation of g prime z is equal to expectation of z times g of z. Okay, so let's look at this side, which is integral of g prime z times. I'm going to ignore the 1 by root 2 pi term before because that is simply not going to matter over here. Uh, Times e to the power minus z squared by 2. Now applying integration by parts. Um, Sorry, this is the minus infinity. Yeah, so applying integration by parts. And of course, we're assuming that at the boundary, which is essentially at minus infinity and infinity, because this is like an improper integral, um, we're kind of assuming that that limit t tending to infinity um, gt e to the power minus t squared by 2 is equal to 0. This is we're assuming this. Um, yeah, we're sort of assuming here that G is kind of well behaved um, uh, at uh, at infinity. So assuming this, then of course, if we apply integration by parts, then this is simply equal to integration minus infinity to infinity uh, z times gz e to the power minus x squared by 2. So essentially, that's how we prove this equality. You can check that the function in consideration over here, which is gz is equal to z to the power n, that will satisfy this criterion uh, at minus infinity. Okay, yeah. That brings us to the end of today's session. Um, Thank you, and see you next week.